Good morning, MA4220 class. It's Sunday morning, and we're going to continue through the variable speed pumping document here. I got the masters on the TV over here, so I may be pausing my presentation briefly to keep up with the boys over there. But at any rate, this is where we wound up last time. And I think we've already really commented on this, but this is a theoretical curve showing probably the maximum on how good this variable speed pumping can be. And we're going to add some reality to this discussion. It's possible that this type of savings may be available, but it's also possible, and in most cases, it's not going to be quite this good, as we will see. Down here at this last paragraph, I think I'll read this. This is kind of starting to get to the crux of the matter here. One of the factors that modifies theoretical variable speed pump power savings, as shown in figure 4 above, which we were just looking at, is the actual proportion of the system head loss subject to change with flow reduction. That would be the frictional head loss in comparison with that proportion of the total head loss maintained as a constant. And that's what I call the static head. And some systems have no static head, in which case we would get a curve like that above, or no constant head. But most, especially in HVAC applications, have some proportion of the total head which has to remain constant, and that will reduce the potential savings from the variable speed pumping. So that's this last statement. These proportions will be affected by system types, and so we're going to look further into that. So under number 3 here, generalized variable speed pumping horsepower saving as affected by system type. So we're right in the middle of that discussion now. And this figure 5 is kind of a trumped up example to show one potential system where all of the head is frictional, and so we'll get this maximum possible savings. So I'll read a little bit here. One such circumstance relates to a closed loop pumping system in which the variable speed pump is used as a temperature control instrument, as illustrated in figure 5. So what's going to happen here is that we're going to maintain the temperature in this tank. We have a temperature sensor into transducer and control, which varies the speed on the pump. So if the tank starts getting cold, the pump pumps faster, and basically we have a heat exchanger over here we're supplying steam to, and so this water comes in. So the assumption here, we've got a temperature sensor here controlling the steam valve, so that this temperature is probably constant. I mean, it could be reset, but for simplicity here, I would say it would be a constant temperature of the supply water. And so if we need more heat in the tank, the pump simply moves more water. If we need less, if we're at temperature, then the pump will slow down. And so there's nothing changes in terms of the flow path through here. And so it's all frictional, or it's all variable head. And so we're going to get the maximum possible pumping savings out of a situation like this. He describes this further down here in the paragraph below the caption. I think we've pretty well said that. The entire system head loss decreases as flow reduces, and that's because it's all frictional head loss. Most variable speed pumps, however, are applied to systems which have a requirement for a maintained or constant pressure difference across the system. And so that starts to limit the potential savings, as we'll see. This last paragraph is pretty good here. The great majority of open systems require that water be raised from a low point to a higher level. The difference in water level is a constant head difference that must be maintained at all times by the variable speed pump despite flow change, or it's a constant head or a static head. A cooling tower with a variable speed pump is a good illustration, as we'll see in the next figure here. So you can see that here's our basin, and this is where the cold water collects at the bottom of the tower, and we're sucking it. This is the suction, so we're showing a straight line. Probably not a lot of fittings, not a lot of loss here into the variable speed pump. And we have some control on this thing. This is our condenser. We're going through this, and we pick up heat in the condenser. We go up to the top of the tower. We spray it out at the high level, and then the water falls through the tower. It's, it's not in the system any longer, so it's an open system. And this H head is the feet of static head in the system, okay? So the closed loop HVAC system shown below, right here, will also require constant head differential at all times. This is for control reasons and to ensure the necessary differential head across any controlled terminal subcircuit is maintained for full load operation. So kind of what they're saying here is that we want to have enough delta P across here. We have to have enough heads so that if any of these control valves opens wide open, we can always get full flow through the terminal circuit. Now, if all of these valves are at 50% and we had a constant speed pump over here, the head would go way up. We would just force our way up on the pump curve, which would be very inefficient. So what we do is, based on the design, we establish maybe it's 20 feet, maybe it's 30 feet, whatever it takes to push full flow through any one of these circuits. We'll set the set point, and then we maintain that differential pressure based on these two sensors. We're showing it here being measured across the third terminal unit. Ultimately, they will all be balanced for the same. In order to balance the system, they're going to be balanced for the same pressure loss. But the one with the highest drop will set that pressure loss, as I think we've seen that before. Okay, so in general, that's what's going on. And notice now we're showing we have a constant speed chiller pumps over here that are providing constant evaporator flow on the chiller. And again, we're starting to see variation in that flow as well. But in this document is old enough that I don't think it's going to show much variable flow through the chiller evaporator. But so this would be, primary water, and this would be our secondary over here. This would be our common pipe. Here's our compression tank and air separator and all that. And so we just have 3 terminal units. These are not primary, secondary. This variable speed pump is pumping this whole network over here. So the primary, secondary, I guess you could call this a primary and this is secondary, but then these are not set up as tertiary loops as we've seen in some of the other materials. Okay, so potential high pressure savings, horsepower savings. Sometimes that HP, I think of that as high pressure, but that's from the steam class, so that's horsepower savings. For both the open and closed systems can be significantly affected by maintaining the required constant differential head or head difference. Variable speed pump power savings with flow change will be the greatest when the constant head difference is only a small proportion of the total head. So the variable head loss dominates. So in other words, if we have 0 static or required constant head, or the smaller it is, the more we can expect to save with variable speed pumping. Okay, so in figure 7, the constant head difference is established by the pressure differential set points across the terminal circuit, B to C. So right here, high side, and on the return side, low side. So we're going to determine by calculations or experience how much differential head we need to have across here in order to be able to fully pump any of the terminal circuits if their valves go wide open. So that's really the game. The variable head loss is stated by the piping head loss. In this case, it's A, which A really, it's from here. It includes this piece of pipe. Okay. So he says from A to B, but I would read that as the discharge of the pump around to B, and then from C to D, which C all the way around through here, all the way back to the suction of the pump. So A, B, C, D is the variable head loss. That when we reduce flow, that's where the energy savings are going to come from. All of that loss, all the fittings and everything in there, if we go to 50% flow, we'll see that head loss drop by 75% or a factor of 4 because of the squared relationship on that. Okay. We have this other figure here, and he's showing the effect of changing ratios of constant versus variable head loss and potential variable speed power savings is shown in figure 8. So there's quite a bit in here. So let's see. So we have our percent flow down here on this axis and our percent full load design horsepower. And of course, the best we could do is have the 100% variable head loss. So there is no static head. There is no control valve head we have to maintain. And as we start slowing that puppy down, it's this cubic power reduction as a function of flow. And so at 50% flow, this is 12.5% power. And that goes back up to that figure 4. That's pretty darn nice. Now, not many HVAC systems with control valves that modulate and all that sort of thing are this good. Okay, on the flip side, if you had a constant flow system with 3-way valves that you're going to have the same flow and you're going to have the same head all the time, I mean, this is the worst it can be. And in the old days, there's still systems out there operating with this. So we're going to have the same pump power no matter how much flow, because if it doesn't go through the coil, it goes through the bypass, so it's constant flow. Now, in reality, there is some pressure drop, but in this article, they are ignoring that. And the pressure drop is if you're 50% flow through the coil, 50% through the bypass, you do have a reduction in pressure. But he's ignoring that in this discussion. And he's saying that no matter where we are. So, if the thing was snapping back and forth between the coil and the bypass, then this would be 100% true. But anyway, for the argument, that's where we are. And so what we see is, so VS equals 100%. That says it's all frictional, no static or no constant head. At 75% variable, 25% constant, we'd say 25% of the head is static or constant head, and 75% is variable. And so on that type of a system at design, if we slow down, we still get pretty good savings. And see, this shows that constant head. So this would show what that constant head is at 0 flow, and so that head is constant all the way up. So anyway, and you can see as we go 50-50 and we go 25-75, And this is no variable head loss, 100% constant head difference. And then this is a constant speed system with two-way valves. So we maintain constant flow through here all of the time, and we simply squeeze off. We have enough power to squeeze off. So the head remains constant, but the flow does go down. On this line, the head is constant and the flow is constant, so there's no change in power. So that's why this is a linear curve, because we're just going linear in flow as it goes from 100% to 0%, and that's the shutoff power, or the deadhead energy on the pump. Okay, so let's see what he's saying here. Should be emphasized that the variable speed pump must work against a high variable head loss if significant speed reduction power saving is to occur. Without variable head loss, the variable speed pump acts similar to the constant speed pump, the only difference being the variable speed pump eliminates the rising pump curve characteristics, because if the constant speed pump is with a two-way valve, you have to ride that pump curve, and as you ride the pump curve at lower flows, then the head goes up. So there is that. So this last paragraph here, I'll go over that. It's evident that in variable speed system design, variable head loss should be maximized and constant head loss minimized. For HVAC application, this means that terminal unit head loss should be as low as possible. Okay, we're going to move on down and look at this figure. We know that since all terminal circuits must be balanced, the highest head loss terminal circuit will establish the required constant differential head. I think I said that. So, looking at this first system here, if this one, furthest terminal circuit had a much higher head loss than this one and this one by some requirement, we could pull that off and treat this as a primary and this as a secondary, which then could reduce the overall control head we have to maintain from the supply to the return. Because now, if this guy was requiring this differential be maintained pretty high compared to what these two guys require, by pulling this off and putting in a secondary type loop over here, then the pressure drop along through here is taken off of this pump and put on this pump, and so we can reduce the overall pressure that we have to maintain. So that's one thing. And the other thing they show is that they've gone from three-way valves to two-way valves to control the flow through these things, which is also a benefit. Okay. And then he starts talking about safety factoring and the fact that pump overheating has always been a major factor relative to excessive pump power draw. So figure 9 illustrates the bad effect of overheating on pump power consumption. This is where, the design engineer designs it. He adds 10% as his factor of safety, and then the mechanical contractor adds another 10 or 20% for his factor of safety. And all of a sudden, if you had a constant speed system, you would wind up clear up here. He's showing here that we have an extra 50%. So this was, the actual true design value, and all the safety factoring went into play. We wound up here, and it could be that this is all we needed was on one of these curves down here, and so we've driven that energy usage through the roof. And so he's obviously arguing that we shouldn't do all this safety factoring. The problem is, though, that if you turn a system on in the field and it can't get enough flow, somebody's got to buck up to increase the size of the pump. And nobody wants to do that. So, that's kind of the conundrum that design engineers have to live with. Okay, so I think that's pretty well through. You need to read this document um, as we go through it because I can't quite reproduce all of his discussions in here, but I think I get the fundamentals out there fairly well. So I'm going to stop this and post it, and then the next time that I do this, we will jump into this Article 4 on parallel systems. So hope you guys have a good rest of the day.